For information, we will have a midterm examination next week. Okay, so the topics we cover are all the truss elements: 1D, 2D, 3D, thermoelastic, and also the stability analysis we're going to cover today. Okay. So besides using finite element to find out the displacement, you need to find the axial force inside the loaded truss. And also, you're going to use the force information to find out what is the axial stress. So the week after next week, then we shall have your first axis session. Since we have missed quite a number of lectures, so we have delayed that session. So we shall revise a bit about this pre-stress cable structure, and we showed this before. Okay, and I think not many of you might still remember. So what we shall do now is show you that a spring which is supposed to support the weight along the axis actually does not support the horizontal force, okay, or vertical force. Okay. So you see here. So if however, if I support on two sides, okay, this spring you can see that it actually still bend into vertical direction. However, if you now doing the stretch of the spring on the support of two sides, you can see the sagging down. Okay, the sagging down which is at the middle. The spring here actually doesn't give foot. Okay. 我们就绕着这些，比如看到没有？同学看到没有 ？So did you see that? So if a spring is to support this weight, it's indeed actually deforming in a curved shape. Okay? So this spring, as we told you before, supposedly is to support the axial force. But now the vertical weight is acting transverse to the length direction. Okay? So how do we do the analysis? So last week we tell you the simple way. Okay? So let's recall what we did before. Okay, if you now write a spring subjected to vertical force, okay, you are writing the equation. Okay, this is V1, this is V2, 2. Then you have K. You have this kind of stiffness matrix. Okay, to describe the vertical displacement under the vertical force 1, vertical force 2. Okay. And now you have a horizontal spring. It undergo displacement U1, U2. And then you write the stiffness the same way. Okay, U1, U2. And 1x, 1, 1. Okay. In both cases, we are talking about the force F1y, F2y, which is passing the axis. Okay? So the formula here remains the same. Okay, the other force, what are the other? The other force is F1x, F1y. They are still passing through the axis. So what you learn here is the linear finite element of thrust. Whenever you are talking about linear, you are talking about a small displacement. Okay? Your displacement along the axis actually doesn't change the shape. Okay? Now here comes the questions. If we now support the spring as we did just now. Yeah. I can clearly see that I'm going to have vertical displacement V2. Okay, V2. So this one is V1 equal to 0. V3 equal to 0. And then my U1 0. U2 nearly 0, I don't know. But U3 is again 0. Okay? So in this case, there are vertical force acting as a meter. Look at here. Can you apply the same equation to write the expressions? No. Why you cannot write the equation using this thrust force balance equation? Because the force direction is not passing through the axis of the spring. Okay, this is actually perpendicular. And not just perpendicular, after the perpendicular deformations, okay, you have the tension effect. Okay, what's the tension effect? So if you now look at the middle point, this has displaced the displacement V2 equal to B. If I now draw the thrust to have the length L, okay, then this will sustain the angular theta. How much is the theta? The theta is D divided by L. Okay? And now if we write the force balance, how can you balance the support to vertical force at the middle? Okay? This can only be possible if the spring acting as a cable is providing a tension left and tension right. Okay? Imagine they are identical, equal length, equal angle. Okay? These are both T. Okay? So what will be the vertical force balance? If you now write vertical force balance, you should write what is the positive part. Positive part is E. Okay, if you draw that force diagram, this is the vertical part, this is the horizontal part, and the vertical part is going to be theta, because the T is changing along the cable. Left cable, right cable are both identical. Then finally, you come to the force balance. Okay. So with this equation, we're going to expand and tell you how much is the deformation. Okay. If you now look at this one again, how much is the tension? If this was the starting length, the new length here is what? The new length here is going to be your U, your V, okay? The new length is L squared plus V squared, okay? So how much is the deformation? The deformation is L prime minus L, okay? Is then going to be how much? The square root of L squared plus V squared minus L. If you do the Taylor series expansions, you can write this as 1 plus V over L squared, and then this is half minus L. So if you do the expansion, you can write this L plus how much? Yeah, this is square root. Yeah, depending how you're going to write. Okay. Okay, so let's see what it will work. Okay, so you can see here. Here you can define the alpha angle depending on the vertical displacement. If this was the starting horizontal line, it's deforming up, okay? Because now it's up positive, right positive, U1 right positive, V1 up positive, V2 right positive, V2 up positive. Then the horizontal truss becomes inclined one. It has an angle of alpha between the horizontal axis and the horizontal line. Okay, this angle will depend on V2 minus V1 divided by the projected line. If the projected line does not change much with the axial deformation, it will appear there. And now, yep, you can write what is your F? F2y, it is T sine alpha. What is your F1y? It is your negative T sine alpha. Okay, if you now do the expansion, okay, you can write your expression here. You have F1x. Okay, so the force balance here is appearing like this. Okay? So if you're going to write the equation, okay, just now my attempt is to find T, but indeed T is to be defined by your this solution. Okay. So what are we going to find? Okay. So indeed your expression here is right. 2p sine theta. Sine theta is your, let's say, if you look at this one. Okay, your B2, B3 divided by the L. Okay, it's going to be P. Okay, so now this is due to the sum of the two parts. Okay, left and right. So if you now do the expression here, okay, we haven't actually doing the division. Okay, you're going to do the division. Okay, another part come from where? Where's another part? This is the sum of T V1. Okay, you see one? Plus T V2 minus okay, we put it positive. This is then the sum. Okay, from here, where do you see your stiffness if you're going to write into matrix form? If you're going to write into matrix form, yeah. So this one, it is minus, depending how you write, okay? Because you have if you have the habit of writing left to right, okay, then you got to write this minus sign. So this one, I think, is not quite right to write this, because you're going to do the expansion. If you're going to do the expansion, you're going to expand it with 3 by 3. Okay? If you're going to expand this, you're going to expand them in this way. Then you're going to have your reaction force, the downward P force, and reaction force 3.我们现在写的这个过程啊，就跟你们平常写的不太一样。我们写的过程是想法普通的方式是把它写成矩阵形式，后面方面你统一用电脑去算。OK， 那目前大概是这个样子。好，再。所以今天要训练什么？训练把普通方程式写成矩阵形式，然后后面一定用矩阵来解。因为我们到时候都是会有这个电脑去算，不过考试的话还是要你实算，所以你那个考试的这个矩阵运算还是要去掌握。So you see here? So this is tension V2 minus 1 over L. Because you know the tension direction is always outward. On the right hand side, it is going northeast. On the left hand side, it's going southwest. Okay? So what you're going to have is F2y is tension times V2 minus V1 divided by L. What is F1y? F1y is negative, even though the angle could be positive angle. Okay, V2 minus V1 tension direction is negative. Okay. With this, then we can do some calculation. Okay. So what's the calculation we're going to write? We're going to see that your horizontal force was close to the tension. 我看一下刚才这张图，因为你毕竟是投影 ，F2x 是什么 ？T cosine r， 它是接近于 T。那你这个左手边就是这个节点，它是 F1x， 它是负 T cosine alpha，it is minus T。Okay， so if you now summarize what you have, the left node is subjected to negative T. Okay, the left node in the y direction is subjected to T over L times minus V2 minus V1. Okay, and then how about the horizontal force on the right node? It's going to be T. How about this vertical force on the right node? It's going to be T over L V2 minus V1. Okay? So with this, you are now able to write your equation into two words. The force, okay, I have to do the correction here. This denotation is not denoting the, this is denoting the unknown. In some old textbook, they are using 1, 2, 3, 4 to denote 1x, 1y, 2x, 2y. Okay, 1, 2, 3, 4 is the which unknown number. Okay. Okay, here after this derivation, we come to two expressions. One is the expression for linear element stiffness. Okay, it is AE over L times, if you look at the non-zero term, they are associated with horizontal displacement. Okay? Got it? And then the other part's got to do with the vertical displacement. This is tension per length. Okay? 1 minus 1 minus 1 associated with V2, V3. And in this way, we define a new term. This is what you call geometric stiffness element, geometric stiffness matrix. Okay? So it has to do the calculation of the tension. 所以同学看到没有？你如果在第一次解的时候，你是没有算你的内部的张力，你是只有线性线。当你算完过后，你有内部张力的，那你再去算这个几何的高度 ，OK？ 那几何高度告诉你什么？几何高度告诉你，听力有了这个张力 ，OK？ 所以你突然可以算出。好，等一下我们会解一道题，大家看。所以这个垂直力就解释，绳索上的这个张力提供你垂直的支撑。Okay, and then next, how do you do the transformation to find out the arbitrary stiffness? Okay, 我们再画一张。 But now with the inclined angle, how do we handle that with the inclination? So this was the something. Okay, you got the U1, you got the B1, and now you got the U2, you got the B2. The angle outcome here, sine outcome is B2 minus B1 over the starting length. If the deformation is small, and then your cosine alpha, supposedly you're going to have your change in the length. So you're going to have your, supposedly you're going to have this change in length. Right? So this is not very precise, right? Just to have your, let's define it in such a simple way. So if you're going to define fully, okay, you're going to have your this deformation, the starting locations. Supposedly, if you're going to describe then arbitrarily, okay. So in this way, okay, let me write this because this is the 0, starting from 0, 0, 0, L. Okay, and now it becomes U1, V1, and then this one is this is L. L plus U2 and then 这东西可以看到它变形。你如果真的是要去展开算它的这个大的变形，你这个可以去展开。So if you're going to explain it full, height change is very simple. Height change is involving the vertical axis. So this is right. Okay, but length change is involving, okay, for the new length, it is what? It is this distance change, okay? This is length change minus U1 squared plus the new height. Your length change, is new length minus old length. Okay. And if you are taking the cosine term, okay, let's see. The cosine term is this length difference. This one is going to be U plus V2 minus this was the information you want to find. 然后我们刚才写的是什么？我们刚才写的是那个 B 项。OK。F1y. This is F1y. Is what? It is your tension divided by the times the negative tension times the V2 minus V1 F. Okay? And this one is the vertical force. So if I now just write this F1y and y, I can write this as a square matrix times V1, V2. So in this case, this is going to be positive PL, this is going to be negative over L. This one is going to be negative P over L and positive P over L. 所以单纯看这个曲线是这个形式。OK， 那我们再看刚才这个水平力，水平力是什么 ？F2x， this is F1x。F1x is negative b cosine alpha. Cosine alpha anyway, because this is horizontal, so usually it's supposed to be 1, 2, 3. And how about F2x? F2x is positive p and cosine alpha. Okay. But not to forget, the important thing here is what makes the tension. The tension here is K negative K U2 minus U1. This is K U2 minus U1. If you rewrite them in the matrix form, F1x, F2x, you're going to write what? You're going to write your square matrix of status and U1, U2. So this one is your negative one. Become positive K minus K minus K K. 所以这个就是我们刚才解的这个真正的原理。刚才就把两个打包在一起写，你很可能会搞混。但是现在把它分拆，那你就比较容易分辨。Okay. Now here comes the question. How are you going to handle? Because up to now, you only able to handle a horizontal truss deformed into a small angle. What about 2D truss? How do you account for the geometric effect? Okay. How do you take care of a stopping rock and then it deforms further? How do you find this stiffness? Okay. Okay. Apparently this is not the 1D truss as it was. 1D truss is very simple. Still, do you remember how do you find your linear stiffness? You know your linear stiffness starting from F1x, F2x is equal to K minus K minus KK, and then This is all axial force. This is your Hooke's law or your stiffness matrix. And then this is your axial displacement. Okay. Remember how do we do the conversions? Okay, if you know the displacement U and V, U1, V1. Because the only thing you care about is your axial part. So if this is bigger, your axial part, your axial elongation is what? Your U1. Your U1 is what? U1 axial is U1 cosine theta. Okay? How about your V1 axial? This angle is 90 minus theta. The opposite angle is theta. So your axial deformation is your what? Is your V1 sine theta. Okay. And then next, we care about transverse displacement. Okay, 这是我们之前解的。OK， 然后，那我大概讲一下我们的这个转换。Okay. So in the case of this, what is your transformation? The transformations using this information, this is your axial. Okay, your axial one. Okay, your axial displacement. Okay, your stiffness. Remember how you write this? Write this into weak displacement V1 x and then U1, yeah, V1, okay. And how this transformation? Remember your transformation? This one is, let's write it capital 1. Let's write it V1, okay? Axial displacement on not 1. And how about the one on not 2? The one on not 2 is U2 cosine theta plus V2 sine theta. So this can be written here. This can be written as, because this is 2 by 1 matrix. So then you're going to have 2 rows. In this case, you're going to have C as 0, 0, and then 0, 0, C as. And then how do you convert the force into the if you now have axial force. The axial force is F1x. Sorry, this is F1. This is F2. You can convert them into 2 components. Your F2x is F2 cosine theta. Your F2y is F2 sine theta. So means if you do the multiplication, multiplication of what? If you do the multiplication of this cosine S00, 0 cosine 0S on both sides, then you are going to get what matrix? This one, the fourth vector become 4 by 2 times 2 by 1. So this is 4 by 1 matrix. This one is 4 by 2 times 2 by 2 stiffness matrix times 2 by 4 and times 4 by 1. Okay? Eventually, it's going to be 4 by 1 vector. So this maps you the equation. Okay? So if you cannot remember this, I recopy this. The stiffness matrix now becomes C squared, CS. I think is it minus C squared, minus CS, something like that. Okay? So this becomes your now new stiffness matrix for 2D truss. Okay? 这个是一个复习，不是今天的重点。那今天重点是什么？你的几何这个刚度矩阵，它如果转是怎么转 ？Okay, in the case of 2D truss, look at here. What is the geometric effect? What is the geometric stiffness? For your 2D truss. In 1D, it is F1y, F2y is equal to this matrix times displacement vector V1, V2. What is V1, V2? V1, V2 are supposed to be the vertical displacement to the rod. I can tell you, rod cannot sustain a vertical loading. A truss or 1D rod can only sustain axial loading. But apparently, using the geometry stiffness effect, it now can sustain a vertical loading. So now, you got to find what is the vertical displacement. Okay? What is the total transverse? We don't call it vertical anymore because it's already inclined. It's not vertical as it was here. It is already angle theta plus 90 degrees. It is vertical to the rod, okay? To the truss. But it is not vertical to the horizontal plane. Horizontal plane is still x-axis. Okay? So what is the transverse motion? Okay? On knot 1, what you can see, your starting is U1, V1. If you're going to find U1 component, okay? You're going to find U1. U1 should have given you a negative component. Okay. This is negative. This is equal to negative U1 sine theta. Okay? And then, how about the vertical part? How much do they contribute to the vertical displacement? They contribute to the positive one. They contribute to positive 1 sine theta. Okay? So now, if you write vertical force using this stiffness, how would I convert it into global coordinate? This is all local. As I tell you, the local stiffness, the local displacement can now be changed. Change to be what? Change to be minus S and then positive. Sorry, this is C. This is the cosine. Minus S plus C 0 0 and then this one 0 0 minus S C times U1 B1 U2 E2， 看到没有？所以我们只是把这个你轴向垂直于轴向的这个在地的位移转换成是这个空间上 x y 的这个世界位移。OK， 所以这样现在只是做了一边的转换。OK， 然后跟刚才转换有什么不同？刚才是从这个转成什么轴？转成 axial transformation， 转成你的轴向。这个转换，in this case, this is what we call the transverse transformation. So it is doing a transformation into the vertical axis. 所以很多同学，你到这个读到硕士，为什么后面会越来越难？你数学越来越难，没有什么，越来越难是难在你当年学的数学是不带几何，你只是背公式。OK， 你对空间上没有感觉，那你如果背公式，零维的没问题，那数学就是一个算式。OK， 那我们现在一维的，零维是什么？01。OK， 所以你如果去叫电机系的来，读电子的做设计，0101，那是逻辑问题。那开始要画电路，这是一维问题，那个两个点画一条线。那现在呢？不是直线，不是垂直线，是一个斜线。你就要开始做这些这个位移的转换。所以为什么讲机械其实比电机难，就是因为你几何上要做转换。OK， 虽然在台湾你做电子行业赚，但是如果站在全球供应链的角度，电子行业是一个低薪、量大的一个产品。什么叫高薪、量少产？人家坐飞机、坐火箭，人家学的是抛线 ，OK 这些 ，OK， 所以这都是全机械问题，只不过是目前没有，但是你在学这个理论上，你还是要处理这样的一个题目。所以你可以选择谈谈OK。It is not just temperature problem which is scary. Displacement field is a vector problem. Okay? Even though you have learned about 1D truss, okay, you have learned about 1D truss. But now if you want to convert it into 2D truss, okay, you have to do the right rotation of the matrix. From 1D to 2D, what you are changing is okay, let's say you have forget about axial elongation. Your transformation will be axial transformation to become 2D. But if you are talking about geometric stiffness, you are talking about transverse stiffness. Your transverse stiffness in the 2D problem got to be subjected to transverse transformation. 你看到没有？这个转换，一个是轴向的转换，轴转 θ 角，是这个 cx 对应 cx， 但是你现在不是轴转，你是垂直于你的杆的轴转90度，这是 minus c sin。还没缴学费啊？OK， 这个转换有点不一样哦，这个是 c， 前面是 cx， 然后后面是 sc。
好，然后这个只是一个位移坐标的转换。那现在我们来看一个例。So if you now look at the force again, how do you do the transformation? You could probably have your axial force here, F1, F2. Okay? This was the axial previously, but now if you want to do the transverse one, you have to draw the F1y, F2y. This is all local. It is 90 degrees to the plus. Okay? But how do you do these transformations into your F1x, F1y? Okay? If you want to do this, you have to draw your fourth triangle. If the rod is 90 degrees of the x-axis, this one must be, sorry, if the rod is by theta angle of the x-axis, this one must be 90 degrees theta. So as a result, what do you see here? You have theta angle here for the force vector. The force vector here is subtending an angle theta with respect to the vertical line. So now, if you do the projection of this force into vertical component and horizontal component, your horizontal component is minus F1y sine theta. What about your F1x? Your F1x is F1y. Your F1y, capital F1y is cosine theta. Okay? So how do you do the transformation? If you now need to do the transformations, okay, you can multiply. 我们来看看你要乘什么。我们来乘一个矩阵，这个是负 s 0正 c， 那这里负 s 0正 c。If you multiply both sides with these transverse transformation matrix, okay, if you do this, you're going to get your new matrix. Okay, 2D matrix. Okay. 所以这个部分感觉很玄，它其实不玄，它只要求你做一件事：空间坐标转换。你空间坐标转换怎么弄呢？请你回去自己画。OK， 这个意思。你刚才交大宿舍，从交大宿舍来到你公务馆，怎么走？当然你现在有Google Map可以带着你走，但是你如果Google Map没给你地图，给你的只是往东多少，往右多少，这样的一个转换，OK，如果不看，让你去做转换，就是这样的一个脑袋，看起来很玄，但是你如果有了图，有了地图，你有了几何，这个方向的转换，看起来就很简单，它是很直观的。反正这个力跟垂直线成立夹角梯，我只把这个力分解成水平力跟垂直力，就这样。OK。那我现在把这个就可以写成 F1x, F1y, F2x, F2y. So this is a force vector which is 4 by 1. On the right hand side, you have the stiffness matrix 4 by 4, and then times the global displacement vector 4 by 1. Now, why do you have to do this? Because I cannot teach you 1D forever. Okay? For structural problem, at least 2D. To be practical, yeah, 3D will become practical. Okay? 所以看到没有 ？OK。你现在的转换是矩阵式。刚才在轴向。In the previously you learned about axial transformation. If it is 2D trans, so you have cosine, sine, minus sine, cosine. Okay, but sorry, this one is cosine, sine, cosine, sine. This is U1, U2, U3. When you learn about this, okay, you have to learn with the proper understanding. Okay, this one.这里我会写大写。那小写的是什么？所以你的走向，画面是。So if you want to do this transformation, okay? The lower case represents the local displacement. 在杆上面，基本上看到的是这个轴向或非轴向。那你这个转换是什么？你说对这个转换不是？你这个轴向，那我们看一下你的。 它是把你的这个transverse one will look like this. Minus sine and cosine. Then this one is, since it's transverse, so it's B1, B2. So it's minus sine.加总在一起就是，所以你们都不要about transformation, you should realize that what's the order you're going to analyze. Okay? You're going to analyze lowercase, this is axial, this is transverse, this is lowercase. Okay? 所以同学看到没有？你的轴的大小正负号，它带的是什么意义？你可能要自己去重新考虑一下。大小写的是，你可以讲成大地坐标，大小就是水平线跟垂直线。所以 this case, the right representation here is axial elongation. Represented in horizontal and vertical displacement. 所以同学听懂，轴向伸长量，这个是张力的方向。它跟你节点上的水平跟垂直位，它是有一些关系，也就是上面这一块有关系。我们先看一旁，这是轴向。那你的垂直方向，垂直方向是不一样。那来源是哪里？来源那个红色的来源呢？红色是轴向，然后就看一下轴向。这就是轴向，然后垂直方
this, now we'll be able to handle geometric effect in the 2D trunks. So you see here, you could apply the previous rotational metric we had. Okay? In the end, the 2D trunks element for linear stiffness, it appears as it would be C squared CS minus C squared minus CS times AE over F. But for the geometric effect, it is S squared minus CS minus S squared minus CS times tension over the length. So this show you what is the right way. 那实际上，其实你也不用完全去背这些，因为你考试你会带一张 A4 size 的那个公式小抄 ，OK？ 但是之所以不开书，就是下周考试我们可以带一页 A4 size 的小抄。开放你带课本跟讲义，理由很简单。往年的话，如果开放你们带课本跟讲义，基本上不会读书。你去了等于，好像很多选择，你下笔就完蛋，你不知道抄什么东西。所以回去先让你准备自己的小抄，要抄什么你自己抄好。所以一张 A4 纸的小抄。带来考试，给你一本书也没用，反正你抄也抄不出东西，还是你自己整理一下你自己的资料。OK， 好 ，So with this, now we can conclude. Your total stiffness consists of two parts. One is the elastic linear part, the other is the geometric effect. So that will be useful for later analysis issue. And then next, okay, can we further expand our derivation? Yes, you can go very detailed. Okay, so the expansion of your issue, if you are not doing simplification, the expansion will be very complex. Okay, so your elongation consists of two parts. If you are using Pythagoras theorem, you eventually can find out your elongation of two ends of the rod consists of two parts. The first part is your axial elongation. The other part is coming from the transverse displacement. Okay. Then you can do the substitution into your expressions, and you can get all of this done. Okay. And then in summary, we also teach you about the rotation. Okay, so the geometric effect will have, supposedly you apply tension, and also you apply vertical loading, and that vertical loading, that tension will contribute to geometric stiffness when it rotates. So this is how you obtain this. 另外加上去的那个机，让我们去做。好，那我们先上到这里休息15分钟。等一下我们会利用这个非线性的分析，去分析你的错觉的力。So later we will use this nonlinear analysis to analyze the bumping loading. Okay. Yeah. With this we are done. We shall have a break for 15 minutes.
这 这里面报。 对，
Okay, the next part, we're going to apply the this nonlinear analysis for the determination of the buffering group. So, see. This is a general expression for force balance for structural analysis. Basically, you are applying the force on the structure, and then the structure will undergo deformation. So the relationship is going through the stiffness. Okay. So in the linear analysis, you only have linear stiffness. However, when you have the stress stiffening, you're going to have both elastic stiffness and geometric stiffness. Of course, for every analysis, you treat with linear elastic analysis first. After getting the tension, then you get extra term. In a way, you can see this is going to be a refinement. 所以这个题目它大概意思是讲，就是说，你如果一开始做线性分析，这是你最粗浅的一个近似解。但你后面你如果因为你有几何非线性，那你的解会比你线性分析的还来得浅。为什么呢？因为你的进度或刚度增加了一个非线性解。So now, how do you do the solving? The solution is very simple. The proper step starts with what? You start with the force. You find the linear stiffness. You got the first displacement. And then next, you increase your force. And then you calculate both the elastic and geometric portions of the stiffness. And then find out what is the new displacement. Step by step, you are finding the changing stiffness, okay, due to the increased loading. And eventually, what do? You sum up all the displacement. Okay? 所以你几何上，为什么说你们一定要学爽？所以你原本你的力时间，你应该是你的力如果是来的很突然。它就直接一个就跳上去，但是你的力如果来的比较渐进 ，so this is a force versus time, this is a time axis. Then you can break up your force increment F1, F2, F3. So the increment here is the F1, the F2. F3. Okay? So you can in that way going to find out what is your total displacement. Okay? 所以这是解非线性的一个做法。Okay? So in this part, then we're going to talk about the critical loading. Okay. So in case of table 1, if you now look at, we only look at one step. Can you in one step find out what is the critical loading? Okay, critical loading is a factor of critical load. Okay? So this will cause your stiffness to vanish. Okay? How does stiffness vanish? Okay, stiffness vanish means that your displacement is going to infinitely high. Okay? So this vanish when the sum of elastic term and this critical load will cause the stiffness to become zero. Okay? So this happens when elastic load plus geometric load, geometric stiffness will cause the stiffness to become zero.
好，这个你看这个解有点复杂，无所谓，我们直接看例题。给那例题我就先用刚才讲的这个例子，我们这个水平的这个针杆或者叫 truss， 形变后，有一个垂直物体，然后后面你得到的这个解是不是什么解？Okay, in the previous case, we tell you the strength can be expressed as axial strength plus transverse strength squared divided by 2. If you now do this interpolation, okay, you can use the shape function. Okay, and if you now do the partial differentiation of the displacement with respect to x, then you got the axial strength. If you do the same, then you got the transverse strength. Okay. And how do you find our stiffness? 我现在是在重复去求你的这个矩阵，不过我们现在用的是能量法。能量法跟之前的差别在哪里？能量法之前的差别就在于，我现在的这个应变不是一个线性线，我还有一个平方向，就是你的垂直物体的平方向。In this case, so the strength consists of two parts. The first part is the linear strength, which is del u del x. The second part, which is non-linear, which is the square term of the del v del x squared divided by 2. If we do the expansion of this, okay, we go step by step. These expansions will go, okay. If you do the expansion, then you can see you have the quadratic term, linear term, quadratic term, and the last term is the to the power of 4 term. Okay? Because if the vertical strength is small, so you can say that power of 4 term is near to 0. Then we can do the approximation. This approximation, we're going to do the substitution of what is del u del x. Del u del x was kind of like interpolated. This 解可能有点让我们觉得让我们再说一次。Okay, so this is not 1, this is not 2. You have u1, you have u2. Remember our interpolation, we tell you before, strength is a function of x. So if starting from u1 here, you can be going more to u2. Okay. How do you get this interpolation curve? The interpolation curve is a sum of two shape functions n1 u1 plus n2 u2. What is the idea of n1 u2? n1 is a space function, okay, times u1. This space function n1 is equal to 1 at x equal to 1. Okay, x equal to 0. But n1 become 0 when x equal to l. So this is the shape function n1 u1. Then next, how about n2 u2? n2 u2 is different. n2 u2, n2 is 1 at x equal to l. But n2 is 0 when it is at x equal to 0. So what is n1 n2? So clearly you can see n1 must be 1 minus x over l, and n2 is equal to x over l. How do we obtain this? We obtain it by derivation previously. We have it before u1 uses the function of ax, a n1 plus
A1x or something like that. This is too long, then you got to express it this way. So by applying the boundary condition, ux equal to 0 is equal to u1, and ux equal to L is equal to u2. This is what we obtain from the shape function. Okay? And how do you derive the stiffness using these shape functions? You are using total potential energy. You are talking about the strain energy minus the work done. Okay? If you now have the force F1, force F2, then you're going to have F1 times U1 minus F2 times U2. This is the way how you find it. And how to find the expression of strain energy is R, the Young modulus, times the strain square dx times the area. Okay. And x starting from 0 to x equals to 10. Okay, this is how we obtain this. And why don't we do the substitution here? What is du dx? Du dx is equal to dn1 dx u1 plus dn2 dx u2. If you do that substitution, you're going to have minus 1 over L, and then u2 d1 plus 1 over L u2. This is then 1 over L u2 minus u1. 同学还记得吗？那你把它带进刚才的公式，带进这个公式。You now have, let's extract the common factor of dA. Okay, and then du dx. What is the du dx? It is your 1 over L squared u1, and then minus 2L squared, and then u1 u2, and then this is the last one. 1 over L squared u2 squared dx. Okay. If you expand them out, okay, yeah, it's up to you whether to expand them out first, or either you integrate first or you find out the force. Okay. What's the first thing to do is differentiation of the u1 is going to be 0, it's going to be del strain energy, del u1 minus F1. Okay? If you do that differentiation, you're going to have dA, and then 2u1 over L1 squared minus 2u2 L2 squared, and then plus the last term dx. Then this is del, this is minus F1. So this integration, because it is a constant, is integrating from x equal to 0 to x equal to L. So you will have 2dA, and then you got now 2u1 minus 2u2 divided by L minus F1 equal to 0. So in the end, you got the dA over L u1 minus u2 is equal to F1. 所以看到，所以这个是你们线性的解法。所以最终你就是得到一个这个 dA over L u1 这是你之前解的。那我们现在看，那你现在会线性怎么解出来？ So how do you derive it for the nonlinear stiffness? 1D thrust. 1D thrust. This is our 1D thrust. You start with what? You start with the starting length, L0. What is your new length? The new length is starting length plus delta L. Okay? So how we manage that? We first have to move U1, U1. Next it has to move U2, V2. So if you do the expansion, your L0 plus delta N squared is equal to what? It's equal to your new position. Okay? What is your new position? The new position, it is in horizontal part. Where is this? This is your L plus U2. Okay, this is your L1. It's starting with 0, 0. This is L0. After that is will and Y is the V2. Where is this point? This one is 0 plus U1 and V1. So you can do the Pythagoras theorem, do the subtraction. 1 plus U2 minus U1 squared plus V2 minus V1 squared. Okay, if you now do the expression of that expression, it was what? L0 squared plus 2 delta L L0 plus delta L squared is equal to L squared plus U2 minus U1 squared plus 2L U2 minus U1 and then plus it depends how much you can go. So you can go So let's see. This is your L0. So if you see that from the first expression, you can solve this term. Next you have your delta N. We are interested to find delta N. How much is the delta N? Okay, you divide this by 2 times L0. Okay, we will have delta L is equal to U2 minus U1 squared divided by 2 times L0. And then this one is plus U2 minus U1 squared. Okay. And then this one, finally you have 1 over 2 L0. Okay, so in this case, because axial elongation is less, okay, this is less as compared to transverse. So now, what can you write about your expression here? telling you if you divide by the chain of the x, right? Then you're going to write what? You're going to write the final expression. Yeah. The chain. Your expression here can be written into this form if you know the finite length. In the case of finite length, you're going to write du dx plus r dv dx squared. Okay, this is our basis. So your expression here for the strength is not linear parts plus the square term of del v del x, but half. Okay, and then how are we going to extract this using your energy method? Let's see. 所以我们现在要做的是一个修正，就是说。我原先做的是线性，那我要怎么修正 ？So I'm going to write in blue color. Previously, I have been analyzing U1, D1 in the displacement field, but now I'm going to analyzing B1, B2. So how much does the transverse displacement change? I write the same. Okay? I'm using the same shape function. Okay. And for the energy function, I got to do something. What should I do? I got to do with the extra square term. So this will account for the nonlinear expression. And what is your dv dx? Your dv dx are the same. It is dn1 dx v1 plus dn2 dx v2. So in the end, it is 1 over L v2 minus v1. Okay. And then now, yeah, you really have to expand the new term. Okay, what is the new term? The new term now is expansion of this. So what do you have? You have EA extracted outside. Now you have du dx squared plus du dx times dv dx squared. And then plus quarter dv dx to the power 4. Okay? And in this case, higher order term in dv dx is 4. Higher order term goes 0. Okay? And then the expression here still remains. But now we have to do the extra term here. Okay? What's the extra term here? Then you expand out. Expand it out. 所以你这一项如果那个实施方向已经取掉了，那你这一项是变成什么？ So you now have what? This is 1 over L u2 minus u1 square plus, this square term. This term is 1 over L, and then u2 minus u1, and then to the power of 3, this is your v2 minus v1 square plus nearly 0 term dx. Okay. If you now want to do the integration from x equal to 0 to x equal to L, the full expression is EA divided by L, and this expression is going to be u minus u1 squared, and then plus 1 over L, u2 minus u1 and v2 minus v1 squared. Now we can proceed to do the zero total potential energy, which is del UE, del U1 minus F1. Okay? So if you do the derivation of the top, then you can find what? You can find 1 over 2 EA divided by L times 2 U2 minus U1, and then times, because you are del U1, this is negative 1, and then plus 1 over L, and then this minus U1, and then V2 minus V1, and then this one is, this one is plus 2 over L U2 minus U1 times V2 minus, no, this one it cannot be derived, okay? So you only have this term. Yeah, you cannot differentiate this term. Yeah. Let's see. Anyway, if you do differentiation with the U1 term, this term are still considered small. So that's why it's 0. Okay? But next, what you can do to derive further, let's see. Remember our force term? Just now we only have force in the horizontal direction, x direction. You can indeed add on force in the y direction. Okay? If that's the case, then if you derive the total potential energy with respect to the meter displacement, then you have del UE del V1 minus F1 y, because differentiation of del V1 del V1 is y. Okay? If that's the case, then you derive this one. Okay? If you do that expansions, now what do you have? You're going to have 3A over M times what? Times 1 over M times U1 times U2 times what? Times 2 V1 V2 minus V1, then there negative V1 del V1。我就看到这个展开是什么像？这展开啊，
那不就是你的张力项 F1， tension 的，给计算到那个到 divided by F， okay， and V2 minus V1， this one is -1， is now equal to your force。所以你们今天学的这个有限元素啊，变来变去，要么是力的平衡，要么是能量的法。那你求到的公式都一样，所以后面你们自己解公式的时候，可以相对简单。反正你们总结出来的公式，能量法也好，力法也好，它得到的答案是一样的。得到与看不到的。So what's different in this energy analysis? Energy analysis introduces you the idea about space displacement. It is changing over time. Okay? It's changing over the space. So when you take in and do the expansion, eventually you will obtain that force. Okay? So it's still going to give you the same equation. Okay? So we are common energy method work as well. Even now you do the new substitution. And next, yeah, this go back to the same equation. And then now we come to the example about the stability analysis. In this example of stability analysis, the questions is what we call simplified one. 这一题啊，它是两个，一个是斜的，一个力，然后那些垂直力是在垂直方向。OK， 这道题啊，只是单纯为了简化解题。OK， 那你们考试题目会复杂一些，这题千万不要当成是就是那种考试的题。OK， 它只是简化，让我们看一下。So now you have 2D truss. One is an inclined beam, which is 45 with respect to the ground, and one you have the vertical column. Okay, and the joint between truss 1 and truss 2, there are vertical force pulling up the structure. Okay, so in this case, how do you write the stiffness? Okay, you can do two steps. There are two stiffness. Okay, the first stiffness you have, 把它涂在考过来。你在看这个解题的过程中，你一定要把你的圆图放在一起，那你才可以想象得到。Vertical line is very simple. You will see for linear stiffness, it is A over L, and this stiffness that is running away. And yeah, this is the one. But now, what do we care? We care about displacement U1, V1. Okay? Defined as not 1, U1, V1. Okay. And then not 2. Not 2 is here.
U2, V2. And then how about the not 3? U3, V3. Because not 3 and not 2 are both fixed. So the only thing that need to be found is going to be your free nodes. Where do you find your free nodes? The free nodes is here. So that's why I circle I square up your free nodes.
所以你的干预矩阵写出来过后，无一非零的这个是 U1 U2，然后这个 U2 V2 是零。
So in this case, yeah, extra denotation, you need to know how to do the it's 0 is the boundary. A is 0. Then likewise, how about the inclined beam? This one is the square pitch line. This is element 1. First element. This one is the second. The inclined one. Okay. In orange. So you know what I mean.那矩阵解法无非就是那些，但是第一步是把那个方程式写出来。这方程式怎么弄出来的？刚才其实已经有上过，有总结过。So how do you get that stiffness of the 2D truss? So here's the summary here. This is the stiffness of the 2D truss for linear elastic part. This is the stiffness of the geometric stiffness. 2D truss. Okay, yeah, it's from there. Okay, after you got that, do the substitution. What is your C? The C is your, what is your C? Okay, let's go back to our derivation. C. C is your sine. With and what's a data engineer? Data engineer is 45 degrees. So in this way, after your substitution, you got your stiffness matrix obtained here. Okay, but I purposely highlight the nodes on the free nodes. Why I care about free nodes? Okay, it's because they are the ones to be solved. You might not be care about other. Yeah. You don't care about other. Okay, you want to find that part. Okay, after you have done this, then let's find the force of the free nodes. Okay. Again, for you, you are not sure. sum the force that you are going to sum. You are summing the force on the free nodes. Okay, you are summing the force on the free nodes. Okay? So in this case, that sum will give you non-zero vertical force and zero horizontal force on the free nodes. Okay? So if you are not clear, then make it. So this force sum is equal to the sum of two elastic force. One part of the elastic force coming from the vertical thrust. One part of the elastic force coming from the inclined to thrust. The stiffness are different. Okay? Then you're going to do that sum. Okay, after doing the sum, you can find how much is the vertical displacement. The vertical displacement is PL over AE. How much is horizontal displacement? It's just opposite. Okay. And then next, how much is your total axial force? You look at the vertical thrust here. The vertical thrust is subjected to the elastic force balance. Okay. U1. Okay. Let's see. U1 0. This is the difference. U1 minus U2. If it happens, U2 is 0. The full expression here should be written as V2. You just have learned that the V2 is 0. Okay. To write the full one, you're going to write this. And this is the expression here. With this, now you're also able to determine how much the displacement in the inclined thrust. The 2D thrust, okay, you have to convert the horizontal displacement into axial displacement. 那我们这个虽然说那个针感水库翼是U1，所以是力是 U1。那你最关心的还是轴向力，所以你要去把它投影。So in this case, your U1 cosine theta is axially inclined. And then your V1 also have the axial elongation, but this is now plus V1 sine theta. Okay. These add up together, then you will have your not one axial elongation, and then minus the angle is 0. Okay. What is 0? This 0 is what is 0? This 0 is it's on the same note.
zero here is because if you forgot your coordinate, you copy it here.你解题的时候不是为了你的算术，解题的时候你要了解它的物理或者力学意义 ，OK， 然后那个数值就代表 ，OK，so this is the part. So after you got all this, one thing for very sure, you have the axial force in the truss point. You have a tension in the truss point. Are there any tension in the truss too? No, there are no tension. Since there are no truss, since there are no stress in the truss tube, the geometric effect only happens in this row. Okay? Geometric effect. Okay? So later, when you are finding the geometric stiffness, you only consider truss element 1, okay, in the horizontal direction. 所以各位看到没有？一个立着的这个杆元素，它的这个几何力在哪里？它如果是立着，几何力就是水平方向；它如果是躺着，几何力就在立着方向。So if you are not understanding the mechanics, this is very confusing. How do you define where you have the geometric force? Okay, the geometric force also the stress stiffening will appear in the perpendicular direction to their tension. 所以你后面解题难不难，不在于你的数学，难不难是在于你的力学跟你的物理。你要知道你的对象是谁，立着杆，它的轴向力是 y 方向，它的水平方向是这个 transverse flow 的方向 ，OK。那如果是躺着，那你到时候再记。好 ，so after you have all done, we now write the force sum on the freeboard. Okay, what is this force sum? This force sum is nothing very special. Okay, I just copy down that force sum again. I'll copy this. What you have to keep looking back for the same equation, for the same statement. It's because if you're going to solve for this, okay, you must realize that what is the displacement that can go very high. OK， 我们来看一下，你现在要找的是水平力，那
给的力虽然是垂直力，同学，你们想想，给的力是垂直力，为什么会有水平位？你如果是错举，老师真的是力不够，哪个同学有大力筋这样子？这位同学，来看。给垂直力产生水平位，你想办法，这么的要学会。不能的话就在桌子上，不要学。
这个
啊，给同学看一下，他说你要倒计时。
我要
不好意思，太紧，我我给你倒计时，拿一个手动的来敲在那个那边，我找一个那个。对，要敲老师可以起。那我们找这里，来，好，那敲老师。扫回去了。老师等一下，还要写字，你们两个我帮我带。对，敲到我没事，对不对？敲到有特别带，啊。有看到没有？给的是垂直力，那断开是这样断。You are applying a vertical force, but the collapse happen sideways. You see that? So in the same question, we may be applying vertical force, but we are looking for displacement in horizontal direction. Okay, supposedly you're going to have zero. Okay, but there is one situation. Okay, you're going to have very high stiffness. Let's see. Okay, U1 is still finite, but U1 will go infinite if the force is in compression. Do you see here? Tension will not have non-zero displacement. Will not have U1 go infinite. Okay? 所以你看到没有？我们这个解题是什么？分子是力，是一个定值，拿出来。那分母呢是杨氏系数再加上张力项。那我现在有一个要求，就是说我垂直力打下去，你的 U1 你的水平位也会爆。Okay, how do you make the U1 go infinite? Or will stick to very high number? It must happen when your denominator become 0. This denominator becomes 0 provided the applied vertical force is negative. If the applied vertical force is negative, means that it is a compression force. So there are no problem doing a pull to cause the deformation, but there will be unstable or instability happen when you give it a compression. So this amount is AE over 1 plus 2 over square root of 2. 好，那顺便评语一下，你们财力读了半天，你解过什么题？辍学的题？你们想过？就是一个脸，就是压。那你没有问过什么？那全天下的人都是垂直受力，那物质还的确是 ，OK， 但是有些结构它不是垂直的，它可能斜杠 ，OK， 那它也承受压力，这样它会不会断掉 ？OK， 所以这个时候，你的有限元素跟刚才讲的二维的那个方向的转置就出现了。这道题是特例，它只考虑垂直的受到的阻力。OK， 另外一个是讲受力。OK， 那这个不是，这个是一个特例。所以如果说题目有变化，你们各种几何
要去求解，不是只有垂直的杆、垂直的柱子才会作曲，斜的也可能会作曲，那取决于它的受力情况。Yeah. So with this, we also tell you the idea, what you call eigenvalue. 刚才的概念是很物理，水平位移不会是，它是一个定值，不会爆，不会变成无穷大。会变成无穷大就有一个可能性，它这个式子，刚度矩阵，这个刚度变成。OK， 那我们现在就连带想到一个数学上的解法。So how do you do the solving to find out the critical loading? Okay, I put it as a lambda star in replacement of P, because P is the real force you apply. Lambda is the eigenvalue, also called the critical loading you apply. Okay? Okay, how do you solve for this? We still go back to the same critical loading definition. In the expression of displacement, you have force over the stiffness. If the stiffness goes zero, okay, if the stiffness goes zero, so this happens when you have zero stiffness. Okay. So you then have the buckling. Okay. Or instability. Okay. So this is whole physical meaning. Okay? If you want to do it rapidly, okay? Okay? If you want this to be done systematically, we now introduce the idea of eigenvalue. What is eigenvalue? Eigenvalue is if you have a stiffness matrix plus a variable term, this sum together will make a system matrix. Stiffness, this is elastic stiffness plus geometric stiffness together. Then the term here, let me change the color. Now I'm interested in finding what makes this the star term. Okay? I'm interested to find out what makes this star term. Okay? This star term will have a determinant of 0. Okay? So if that's the case, then you'll be able to find the critical loading. So this is then repeating what we did, but introducing you the idea about eigenvalue. Okay. And then eigenvector is the way it gives way. Okay. 就像刚才这个断两段，它是一个其中断裂的一个基础。Okay, with this, then we are almost done. And then, by the way, I will spend some time revising your tutorial question. Okay, just to give you an idea. 我们课基本上完了，但是这个考试的部分比较往第三。
the written examination will be scheduled on next Monday. So the topic to be tested include the trust element, the static analysis, 1D trust, 2D trust, 3D trust, and then energy method and distributed loading, thermoelastic analysis, geometric nonlinear stiffness. That's the including today part. So the examination will be restricted open book. You are allowed to bring one A4 size paper or formula. Let me edit that. Formula. Okay. Okay, you're going to do your own preparation on that. And next, then we'll come to the answer. So we have done how many, Dorian? How many homework? Let's see. So we have done two homework. This is compulsory. Okay. Then all carry marks. Okay. Let's see the answer. Okay, the question one. Okay, let's see. You basically have quite a number of trust elements. You have trust 1, trust 2, and trust 3. Let's see. 1, 2, let's see. Let me circle the trust element. One, two, three. Okay, the value here are all different. So that you in the analysis, okay, how do you do that? Okay. You define element 1 using not 1, 2. Element 2 using not 2, 3. Element 3 using not 2, 4. Okay, the stiffness are different. K1, K2, K3. One thing we notice is not 1 is fixed, not 3 and 4 are fixed. These 3 knots, 2 are common. Okay? If that's the case, how do you write the solution? Okay? We can write force balance on each node. But the issue here is internal force on element 1 is unknown and is to be determined. And element 2, they are also force balance. Okay, their internal force are unknown. And then element 3 also force balance. Internal force unknown. Okay. But now, if you do the summing of the force, okay? If you do the force sum, left node is reaction force. And then the middle nodes, that way you do the sum, are subjected to a force P. Okay, this is the applied force. Let's draw that. This is the applied force. Apply external force. 所以你们这个力，你还得要分什么叫内力跟外力。内力这个你知道。 但是外力它是比较会给。Okay. So if that's the case, and then also you don't know the reaction. So there are quite a number of forces. Yeah, this one could be also a reaction. So with this, then how to do the solution? Okay.
所以你们要去解啊，
不是叫你们去像他这个，你要解的话，你可以去算，OK， 合起来可以。So this is the left reaction. Another important thing is when you are doing this, please do circling the force. 那你们现在因为这个动笔的机会很少，你如果不动笔，这道题大概是做不下。OK， 动笔是把你的那个 idea 给它合上来。So with this, now there are only one knot which is free. That is the knot two. Okay. Then you do that sum. Okay, you can do the complete expressions. So element 1, element 2, element 3, all sum up to be external force. This is reaction force. This is applied force. The other two are the reaction force. Okay, then now the sequence matrix, you do the sum, this is the expressions, and now you realize the other notes 1, 3, and 4 are all fixed. The only free notes is U2. As a result, after you do the substitutions, find how much is U2, you put the applied force divided by the sum of the sequence. So with this, we are done with the solutions. And then next. What do we do next? We do find the reaction. Okay, reactions. Reaction happens where the displacement is 0, but by substituting Q2 into the first row of the expression, we find the first reactions. By substituting Q2 into the third row of the equation, we find the third reactions. By substituting Q2 into the fourth row of the equations, we find the reaction out of F4. Okay? And then next, and these are the two strings in series. First element have knot 1, 2. Second element have knot 2, 3. They are both subjected to internal forces. But now, if you do the sum of them together, knot 1 is subjected to reaction. Knot 2 is free. Knot 4 is subjected to a cooling force. In this case, rather than providing a cooling force, I apply the finite displacement. This is a constraint displacement. Then I can find how much is the F3. If the constraint displacement is even, then the block force can be solved. Okay? So after you do the substitution into the expression above, okay, you can find what is your U3. Your U3 is delta. Okay? This way you can find this is the block force. Okay? 所以有时候解题，你要知道你题目那个要你找的是力还是力。那你现在给的这个叫 constraint 约束，有人约束力，但你要找到的是你的这个抵挡你的这个力，这个叫 block force。所以名词的定义很重要是在哪？就是说，你在这个
后面的题目后面的物理现象越多的情况下，边界越多。你如果不知道名词定义，那你很可能就不知道要找什么答案。
And in the third question, you have two identical truths but mirror each other. So you are asked to what? You are asked to find what is the vertical and horizontal displacement of the three nodes. On the three nodes one, okay?
你要给它这个节点有一个属性，一般它不写，但你自己还是得写，就叫 three nodes one，OK？、那你不写的话，很可能就是说，你就瞎的把那个边界条件跟位置点放在一起。
The three nodes one. So what's the first step? Defining the element. The first element is define
都往，为什么？你为什么不选择一、二？你如果选择2、1，它跟水平线夹角是60度。你如果选择1、2，它跟水平线的夹角是多少？360减掉120，就是210。所以你这个坐标的选择啊，你通常要选。那另外一个。How about 3, 1? This is the case that showcase you should not